Hi, everybody. In this lecture, we're going to take a look at a different type of oscillating system, the pendulum. So everything we've done so far has been a spring mass system. It's all been about masses bouncing back and forth or up and down on the end of a spring. What about something that swings, that doesn't move in a straight line, but moves in an arced path like a pendulum? So you can see on the screen in front of you, there is a simulation. Since we're virtual, I can't actually get a real pendulum out here, but we can see in the simulation the ability to create a pendulum. We have just a mass on the end of a rope, and I should be able to pull this thing back and let it go, and just like a real pendulum, swings back and forth, oscillates back and forth according to the laws of physics. Now, what's kind of neat about this is I can alter gravity, I can change the mass, the length, and add friction. So one thing you'll notice, this thing's just going to go forever, back and forth, and you can kind of see these lines, little tick marks right here showing its oscillation. But if I make it a little more realistic and add some friction, just like a real pendulum, which has some rubbing and some air resistance, we see that the oscillation eventually dies out. But we should see some connections right away to things that we've already studied. This is very much like the spring mass system, and we can see this dotted line in the middle is kind of a giveaway. There's an equilibrium position that if I put the mass in that position, it doesn't move or it doesn't oscillate. And it's when I pull it away from the equilibrium position that there's a restoring force pulling it back towards equilibrium. Now, what's different is the restoring force now is not a spring restoring force. The restoring force for the pendulum is gravity. Gravity pulls it back towards equilibrium. We can kind of see that because forces cause accelerations. I actually have the ability to see acceleration on this graph. So what I'm going to do is I'm going to hit the pause button here so that it can't swing. And as I pull this back, you can see that force of gravity pulling it back to equilibrium, that acceleration is getting bigger and bigger the farther back I pull the mass. Okay, now the mass always weighs the same amount. It turns out that it's just the component of gravity pulling it back towards the dotted line, as we'll see later, is increasing. But this feels very much like the spring mass system. It gets pulled back towards equilibrium, and if I bring it over here, it gets pulled back towards equilibrium. Now, there are a couple of differences, though. I want you to notice for the spring mass system, the farther back you pull the spring, the larger the force gets. And it just keeps getting larger and larger in this linear relationship. And so we see this kind of like that. It's getting bigger and bigger. But I want you to notice that as it starts to hang vertically, it still gets larger, but it gets larger at a very slight, almost unnoticeable rate. I mean, the amount of force it has for all these angles really doesn't change very much. But it's down here where it changes by a lot. So the pendulum is going to be a pretty good example of an oscillating simple harmonic motion for small angles, but isn't going to work so large for large angles or work so well for large angles. Now, before we leave this simulation, I want to take a quick look at the question from the bell work about Tarzan and Jane, because we can actually simulate that here and see what the answer would be. So first I'm going to get rid of friction. I'm going to add a second pendulum, and I'm going to make them both have the same length. And just to exaggerate things here, we'll make one mass really small, the red one really small, and the blue one really big. Okay, so everything's paused. What I'm going to do is I'm going to take this, I'm going to pull it back, pick some distance, I don't know, about 35 degrees. Take this one and pull it back 35 degrees. I don't really need that, get rid of that. And when I hit play, they're going to let go. And it'll be like Tarzan and Jane swinging down. So everything else is the same. The length is the same. There's no air resistance. The gravity is the same. It's just the difference is the amount of mass. So what did you think for the bell work? Did the heavy object get there first? Did the light one get there first? Or was it the same time? Let's see. We'll go to slow motion so we can see this clearly. Watch carefully. Here they go. Down, down, down. And wow. It's like they're glued together. There is no difference between the two motions mass, the motion of the two masses based on their mass. So if you thought they both reached the bottom at the same time, you were right. And a good way of thinking about this is we know that objects will free fall at the same rate regardless of their mass. The same thing ends up being true for the gravity-driven pendulum. Now, in order to change the rate at which this thing oscillates, let me go back to my normal rate right here. One way that I could get them out of sync with each other is by changing their length. So the mass doesn't matter. I can make the mass exactly the same and they stay the same. But what if I take the red pendulum and make it shorter? Okay. As soon as I make it shorter than the other, we notice that it oscillates much faster, more oscillations per second. that makes a difference. The other thing that you can do to change the rate of oscillation is change gravity. If I make gravity stronger, notice how both the pendulums go faster. There's a bigger restoring force pulling them back to equilibrium. And if I make gravity weaker, it's a little more anemic, a little less pull. Okay, and in fact, if you take gravity away, well, heck, if I take gravity away, they're just going to go flying off. But let's take gravity away and just pull them back and let them go. So yeah, they're not going to oscillate at all. There's no motion at all. So one of the things that engineers have actually done is they've designed really simple, sensitive pendula in order to measure the acceleration of gravity. So if you're walking around on the surface of the Earth, the pendulum might go a little faster or slower when you're near something gravitationally attractive, like a mineral deposit underground or something like that. It's pretty wild. All right, let's go to our notes now. Not a lot of note taking today. It's pretty quick. We got, put it up here on the screen. We just have a couple new formula to develop and add to our 3x5 and try to make a connection to what we already know with simple harmonic motion. So the pendulum, let's begin by drawing a picture of the pendulum. So we got kind of someplace to anchor it, say the ceiling, and we kind of draw a dotted line right here. The pendulum also has an equilibrium position. Let's draw an imaginary spot for my pendulum here. This is just like the spring mass system, the place where it will stay at rest if you leave it there. If we take this thing and we pull it back, say we pull it back over here, this location, then it's going to want to swing down over this arced path, pick up speed. When it hits equilibrium, it's going to go super fast, and it's going to swing up the other side. So we got kind of a positive and a negative amplitude back and forth on either side of equilibrium. Now, in terms of the forces that are acting, it's a little bit more complicated than the spring mass system because we have a tension force from the spring, a tension force, and there's no spring. What am I talking about? There's a tension force from the rope, and we have a gravity force pulling it. And so technically, neither of those two forces is actually pulling it forward along this arced path. Well, tension doesn't at all. The tension force does no work, doesn't affect this thing at all. It's at a 90-degree angle to the motion, but a piece of gravity does. So if I pull my pendulum back to angle theta, I can take my gravity force and I can break it into components. There's a part of gravity that's pulling outward and a part of gravity that's pulling forward along this path. And it's this forward piece that matters to me. This angle right here is the same as the angle theta that this thing's pulled back. The force of gravity is just the weight of the pendulum, so that's going to be equal to mg. You can see that I have a little right triangle here, the hypotenuse being mg, this angle being theta. So it's the opposite side from this. So the side in question, mg sine theta, the component of gravity pulling me back towards equilibrium. So one important thing to recognize about the pendulum is not technically simple harmonic motion. It's just going to be an approximation. The restoring force, it does have a restoring force pulling it back to equilibrium, which is why it oscillates, is equal to a component of gravity, mg sine theta. And the reason it's not simple harmonic motion is this is not a linear equation. If you double the distance or you double theta, how far back you've pulled it, you're not going to double the amount of force. It ends up being a sine relationship. And so just to kind of illustrate what I mean by that, come up here, think about what a graph of sine theta looks like. So this is sine of theta as a function of theta. The sine function looks something like this. Now, you can't pull a pendulum back through any angle you want. I mean, the farthest back you can pull this pendulum is through a 90-degree angle. So 90 degrees is actually right here. So it's really just this first part that we're looking at. And so we do see that the force is going to grow. It's going to get bigger and bigger, but it's not linear. Well, here's the interesting thing, is it's kind of linear. At first, it looks pretty linear, but then the farther back you pull it, it starts to depart from the linear relationship. and starts to look like a curve, and we start to get a different mathematical relationship, and really need some pretty complicated differential calculus in order to solve for how this will behave. So what we're going to do, we're going to actually take advantage of this fact that the sine function is pretty linear as long as the values of theta are small. So here's the big idea. We're going to make something called the small angle approximation. If theta is small. Now, small is a little bit subjective. I would say, kind of rough rule of thumb, anywhere from like 0 to 15 degrees that you pull the pendulum back. Then theta is going to be approximately the same thing as the sine of theta. In other words, this red linear graph, this red linear line, this would be theta as a function of theta, is basically the same thing as the sine of theta for small angles. And I just want to point that out. Whenever you see a pendulum that's keeping time, like on a clock, you'll notice that pendulum clocks don't swing through huge angles. They tend to swing through rather small angles in the range of 0 to 15 degrees because they want to go through simple harmonic oscillation, nice predictable time. And if that's the case, then that means that the restoring force is going to be not mg sine theta, but just approximately mg theta. And that is linear. So with the small angle approximation, we do get simple harmonic motion as long as the pendulum just swings through small angles. So I'm not going to do all of the math to derive this equation, but we end up with it's not surprising, we get a very simple, similar relationship to that of what we got with the spring mass system. And we're going to add this to our equation card, and then we'll be done. The period of a pendulum, a simple pendulum, so a simple pendulum has all of its mass concentrated at the end, and it's just moving through a small angle with no friction or air resistance, is equal to 2 pi times the square root. This looks super familiar, doesn't it? It's just like the spring mass system, 2 pi square root of something divided by something else. Now here's what's different. The pendulum does have mass, but what we saw in the experiment with the Tarzan-Jane question, the mass doesn't matter. Turns out mass ends up in the derivation being part of both the numerator and denominator, and it cancels out. So the only two variables that affect the period of an ideal pendulum are the length and the strength of gravity. So just like the spring mass system, where we've got mass, which is a measure of inertia, and then in the denominator we've got K, which is part of my restoring force, I have some inertia in the numerator and a restoring force in the denominator. So the restoring force is gravity, and the inertia, well, think about it. Restoring force is gravity, which depends on mass, and the inertia depends on mass. That's why it cancels out. The L stays behind because really long things are harder to swing back and forth than short things. And we don't really get into that in physics 1, but anyway, it comes out in the equation. You'll just have to take my word for it. Okay. So this is the period for a pendulum. And what I would suggest also doing is adding the equation for the frequency of a pendulum, just like we did for the spring mass system. The frequency is just the inverse of the period. So instead of 2 pi, it's 1 over 2 pi. And again, make sure you put that 2 pi in parentheses, divided by the square root of g over L. So it's just the inverse of the period equation. And so pendulums are great for keeping time. Anything that's going to oscillate back and forth is good for keeping time. So a pendulum, nice way to do that. If you know the strength of gravity, then you just tune the length to produce the period you want. You got the tick-tock for your clock. Or as I mentioned before, if you know the length and measure the period, you can solve for gravity and figure out how strong gravity is where you are, what the acceleration of gravity is. The last thing I just want to comment and just kind of point out explicitly is that the period of a simple pendulum doesn't depend on mass. Doesn't matter, like the spring mass system does depend on mass, but not the pendulum, or amplitude. Amplitude, how far back it's pulled. Now, I gotta say that with a caveat. I gotta say kinda. The last one is kind of true, because if I do pull it back too far, say more than 15 degrees, then it's not going to follow this relationship, and I could end up with different periods So just be aware that as long as you're moving through a small range of angles, the amplitude won't matter. But once you get too big, it throws everything off. There you go. That's all there is to say about pendulums for our class. You get a chance to try some homework and practice this, and we'll see you next time.